All right, so for 2a, if you're finding the area of a function, or of a region, right, you are just integrating top function minus bottom function. Or if it makes sense, like for example down here, you can actually do it either way. You can do top minus bottom, or you can do things in terms of y and do right minus left. Like you could do either one there. Doesn't matter which one you choose to do for that problem. I'd probably still do top. Well, the advantage to doing this right minus left, it's much easier to integrate if you do it right minus left, because where you got a square root right here, if you solve for x, you're just going to square both sides, and then you don't have like fractional exponents to deal with. So it is actually easier to do that in terms of y than it is x, but it can be done either way. It's not terrible either way. In fact, when I do the key for that, I may do that both ways so you can see the difference. Let me go ahead and save this as my key so I don't have to rework these parts that I'm working right now. That'll be smart of me. Alright, so for this one right here, we're just doing integral of the top function minus integral of the bottom function, but I do need to know which one's top and bottom, and they did not label these for me. However, if I'm trying to figure this out, what shape do I have for 2x squared minus 6x plus 4? It's a quadratic. Is it a happy face quadratic or a sad face quadratic? It's happy. Which one has to be the quadratic here? The bottom one. So this function right here, the one I'm highlighting or tracing right here in purple, that has to be f of x. And then the other one right here is g of x. And so if they're asking me for area, if it's 2D, you're just setting up integral of top function, which is going to be 4 cosine of 1/4 pi x minus the bottom function. Make sure you put some parentheses around here. 2x squared minus 6x plus 4. Honestly, actually, those are two very different equations, right? So you can do them together, or you can do them as separate integrals. In this particular case, I think I would prefer to make these separate integrals. Pull the x right here. That way, you can kind of do each one separately, think about them independently of each other, and just subtract your answers. Sometimes it's helpful to put them all together because you can combine pieces of them. You can't really do that here, right, where one is a trig function and the other is not. What should my limits be? 0 to 2. So 0 to 2 for both of these. So a lot of the challenge in this problem is just in evaluating here, because this is the only piece that you do actually have to solve. So over here I'm going to do the right side first. It's easier. I just have to integrate this. That is going to be 2/3 x to the third minus 3x squared plus 4x. And I'm evaluating that from 0 to 2. And then I'm going to plug in. I will have 2/3 times 2 squared or cubed minus 3 times 2 squared plus 4 times 2 minus, is that alright with you guys? But just put a 0 right there. You're going to get 0 when you plug in 0 for that one. Be careful on the other one. You won't. I don't have to simplify that. I think I might, just because I think whenever you have the FRQ quiz, it is a lot easier to remember that the answer is 4 pi plus 27, and then you can know that you were right than if you don't. But on an actual exam, I don't think I would simplify it. So I'm going to leave it for a second. We might come back and simplify it. On the other piece, okay, how do I integrate that cosine function there? I can pull the 4 out. I would definitely do that. But it's just a coefficient. So I can take that 4. I can move it out front. And then when I integrate cosine, what do I get? That's a derivative. Sine. Positive sine. But I've got this extra stuff right here in the middle. Right? So it's not just cosine of x. It is. So when we're integrating, there's not really a chain rule. If it's like, if you're taking the derivative of this, it would be called the chain rule. When we have to integrate something that would require the chain rule, it's a u du substitution, right? So we're going to let this part right here be our u. So u equals 1/4 pi times x. So what is du? What's the derivative of 1/4 pi times x? 1/4 pi, because pi, even though it doesn't feel like it, is really just a number, right? And a dx. I would even call this pi over 4 just because it makes it a little easier to put that number in there. So your dx over here needs we need to add a pi over 4 right here. If we put a pi over 4 here, what do we have to do on the outside? We have to multiply by 4 over pi. So we are going to get 16 over pi integral of cosine of u du. Now, you have two options here. You can stick with the limits of 0 and 2, but you need to put x equals. Or the better thing to do here is convert your limits, right? So for the 0, u would be 1/4 pi times 0. That's just going to give us 0. So the bottom limit stays 0. And for the top limit, I would have 1/4 pi times 2, which is going to give me 2 pi over 4, which is just pi over 2. And now that I'm like looking back upon this, I really wish I had just done these two pieces completely separately and then subtracted their answers at the end, because everything's not quite lining up. The left side takes more room for that, but it's fine. So I've got here, when I integrate cosine, I get sine. So I have 16 over pi sine of u from 0 to pi over 2. You do not have to go back to the limits for this. In fact, let's do this. I'm gonna erase all my negatives, and I'm gonna just draw a line right here so that I can do this separately, and I'm running out of room, and at the end I will subtract my two values. So this is going to be 16 over pi sine of pi over 2 minus sine of 0. And so that is 16 over pi times, what is sine of pi over 2? Unit circle. Right here at pi over 2, you got the coordinates 0, 1. Sine's the y coordinate. So you got 1 minus what's sine of 0? That's right here, y coordinate 0. So we just get 16 pi. And then if I simplify what I've got over here, I've got 2/3 times 8 minus 12 plus 8. So that is going to be 16 thirds minus 4, which will be 16 thirds minus 12 over 3, which will be 4 thirds. So, area of R is going to equal 16 over pi minus 4 thirds. That'll be your final answer there. I'm interested. Did I put which? 2013 85. Let me look at the solutions for this. For this question, you get a point for setting it up. A point each for each antiderivative. So integrating the cosine part correctly and integrating the 2x squared minus 6x plus 4 correctly, those are separate points, and then a point for your final answer. So even if you struggle on that U to U substitution, you can get 2 points with just the setup and the integrating the part that just has the x's. Let's go ahead and do B. And this will be our first example for the type of notes we're going to do today, because I want to make sure we do this one since it is this last thing. So it says, write but do not evaluate an integral expression that gives the volume of the solid generated when R is rotated about the horizontal line y equals 4. Okay, so if I go up here to this graph and I draw in the horizontal line y equals 4. That is right here. There is y equals 4. And we will be taking this area, our area for R, and we're rotating that around. That line, y equals 4. Will this have a hole in it? Yes, it's going to have a hole in the middle. So that means we got to do volume of the outside minus volume of the hole, right? So, I mean, it's not going to hurt anything if you write volume of outside minus the volume of the hole. So, here's where it's different today. It's different, but it's the same, okay? So, I was telling you guys yesterday that you always want to start from the line that you are rotating around, right? And then you want to draw yourself a line out here to the furthest away point, right? And that can be your capital R. Are you going to do this in terms of X or terms of Y? X, because this is a horizontal line, right? Anything horizontal, it's going to be in terms of X. Thank goodness, because if you had to solve these for Y, it would be a nightmare. I think it can be done, but it would be terrible. So, when I'm doing that capital R of X, I want to do top minus bottom, right? So, what is my top? 4. What is my bottom? F of X. And you can call it F of X. So, that capital R of X is 4 minus F of X. As long as they have used function notation, you can call it F of X. You don't have to put the equation, but you could. I think you're okay here because you're using it as a function, whereas R is just like naming a region. So I think you're okay. R is not really a function itself. It wouldn't hurt if you're nervous about it, like, because you do want to be careful with that, like not repeating variables that are used. So if you wanted to use a different letter, you could there, but I don't think it will matter in this particular case because R is not a function. If they had like a capital R of X, which I don't think they would do on a problem like this, then you would need to make, like if they had named one of those functions R of X, then definitely pick a different letter for your radius. But they'll probably stay away from it because they know R is typically used on these type of problems here. So you can do the equation right here. If you do, make sure you got parentheses because that negative has to get distributed. But if they've named these f of x and g of x, you don't have to evaluate, right? You just have to set it up. So use f of x and g of x. It's easier to do there. So for this part of the integral, we're going to have pi integral of radius 4 minus f of x squared dx. What should my limits be for this? Zero to 2. X-axis, 0 to 2 over here. Okay? And then we need to do the volume of the whole. So the volume of the whole, if we go up here, for our lowercase r, you want to start at, always start at the line that you're rotating around. Go to the closest function. That's your lowercase r. And then think, top minus bottom of that line, right? So what is the top on that line? 4. What is the bottom on that line? G of x. So your lowercase r is going to be 4 minus g of x. And you should see like some symmetry here in those two radii. Like if you got a number minus a function, the other one's also going to be that number minus the function. Like you're not going to see those switch there. Although because you're squaring, you can get the right answer even if you switch those. But I think it's better for us to write it this way. So we will have integral from, oh, don't forget your pi, integral from 0 to 2 of 4 minus g of x squared dx. Yes?
If you write out the capital R of x equals 4 minus f of x, could you just write pi integral from 0 to 2 of capital R of x minus
Probably. Yeah, probably. If you do that, I would probably, I did leave off my R of x right here. But yeah, I think that would be okay. If you have specified what they are, and then you just do pi integral from 0 to 2 of capital R of x squared minus pi 0 to 2 lowercase r of x squared. I think that would work. There. Now, if you look at the key for this, zoom in because you can't see that. If you look at the key for this one, they put them together, right? Their two integrals are put together. And then they plug this back in. But that's not going to be required, right? You could do them separately and put a minus sign in between. Now, if it's a multiple choice question, this is probably what it's going to look like. They're probably going to put them together. So it's okay if you want to. Or some of you may be even setting them up like that from the beginning. That's fine. But if you have them separate, you're fine. So you could stop here. You would be done for that. So it's really like what we were doing last night, except for last night we always had a 0, right? Like you would have, when you were doing your capital R or your lowercase r, it would either be a function minus 0 or 0 minus a function because we're rotating around that x-axis. For these problems, it's going to be a different number than 0. Okay, so I do want to go back up here and look at B on number 1. So this takes a total mind shift, okay? Because if we are looking at the region R has is the base of a solid. The cross sections perpendicular to the x-axis, have an area A of x equals sine of pi over 2x. Find the volume of the solid. When you see cross sections perpendicular to the x-axis, first of all, that tells you, x-axis tells you this is a dx problem. And cross sections perpendicular to the x-axis, this is where we did like a s value, right? Which was different. And for most of the problems, we had a shape. They told us it was squares, or it was rectangles, or it was this. So if it was a square, we used s squared, right? If it was a rectangle with a height of 6, we did 6 times s. If it was a triangle with one leg in the base, right? Isosceles triangle with one leg in the base, we did 1/2 side times side, right? All of those. So this one is weird because it tells us that the area is just sine of pi over 2x. So whatever the x value is, we just get the sine of pi over 2x. That's our area for that. So for this problem, where we normally were doing like a of x, or a of x equals, and then we had like our s squared, and then we plug stuff in, this is the formula for area that you are using, right? This is like your area of a square, your area of your circle, or area of your triangle. So if we look at our picture, I need to look at the key for this. Them not using a different variable. This might actually be even easier than I'm thinking. What year was this? This was 2009, maybe 4. Yeah, okay. So, here, this is actually much easier than the cross-section problem because they've already given you the area, and it's in terms of x, right? It doesn't have like a s or anything in there. So, they've given you the area formula. You just need to integrate for the interval that you need to look at, which for this problem, you're looking at x-axis is 0 to 2. So all you're going to do for this problem is you are going to integrate from 0 to 2 sine of pi over 2x dx. And this is going to be a small u du substitution, right? Your u has to be pi over 2x, which means that du is going to be pi over 2 dx. So I need to put a pi over 2 right here. What do I have to do out front? Flip it 2 over pi. So this piece right here, this piece right here, that's my du. So if I convert this, I've got 2 over pi integral sine of u du. I would convert the limits, then you don't have to go back to x's. So when I plug in 0 here, pi over 2 times 0 just equals 0. So 0 stays the same on the bottom. For this top limit right here, 2 times pi over 2. 2's will cancel right there. I'll just get pi for that top limit. Okay. What do I get when I integrate sine? Negative cosine. So this is going to be 2 over pi times negative cosine of u. and I will evaluate that from 0 to pi. So 2 over pi times negative cosine of pi minus negative cosine of 0. Here's one of those you got to be really careful about, like saying it's going to be 0 when you plug in 0, because what is cosine of pi right here? Negative 1. So I got 2 over pi, and I've got negative 1. I'm going to go ahead and change this to a plus right here. And then I've got cosine of 0. What is cosine of 0? 1. So this becomes a positive. So I've got 2 over pi times 2. I mean, technically you could stop here. You don't have to combine these, but it's pretty easy combination. So it's going to be 4 over pi as your final answer on that. Questions there? If you have a cross-section problem and they give you a formula for area, you're pretty much just integrating whatever that formula for area is. Now, most of them you have to come up with it on your own. I think it might be beneficial for us to go look at one of those problems where you got to come up with that area on your own. So, questions here before we move on? All right, let's go to, do a little bit off. Let's see. Let's do C. Region R in the base of the solid is in the base of the solid. For each y where y is between 0 and 6, the cross section of the solid taken perpendicular to the y-axis. So perpendicular to the y-axis, what's that tell us? It's a dy problem, right? Is a rectangle whose height is 3 times the length of its base. So these are the ones where we use a S. We're not thinking about rotating. There's not going to be a pi unless you're talking about semicircular cross sections, right? So no pi's in this. We've used a lot of pi's. Pi's are for when you're rotating, right? Cross sections don't have pi's unless you're using a circle or a semicircle as your cross section. So if I want area, I need A of y, right? If I want area of a rectangle, right? I'm going to go back up here to my picture real quick. Okay. Perpendicular to the y-axis means that I'm going to have a line that goes across here, and I'm going to call it S. And I'm going to measure that, and it's going to be like we did with those little squares. I'm going to cut that out, make a rectangle. What's the height of that rectangle going to be? If the bottom is S, what's the height going to be? 3S, because it tells us the height is 3 times the length of the base. Okay, what's the area of that rectangle? 3S times S, which is 3S squared. Okay, and so your S just goes across the figure. It's not necessarily to an axis. Now, in this case, it is because the way the picture is, right? But it doesn't have to be to an axis, right? It's just across the figure, either horizontally or vertically. For that, so I got 3S squared. So now I need to know what S is. S is going to be whatever I get when I do right minus left. So S definitely is going to be something minus 0. I could be wanting to call it 2 square root of x, but is this a dx problem or a dy problem? Dy. So I have to take y equals 2 root x, and I got to solve that for the x. So I got to divide by 2. Y over 2 equals the square root of x. I got to square both sides, so that is going to give me y squared over 4. It might actually even be a little easier to think of this as x equals 1/4. Y squared integrating is a little bit easier, even though, do we have to find it? No, we don't have to actually solve it, so you could write it either way. It's actually easier to write as y squared over 4. Right, so right is on y squared minus 4, left is at 0. And so I'm going to plug that in. So I got y squared over 4 minus 0. I'm plugging that in. A of y is going to be 3 times y squared over 4 to the second power. Okay, for cross sections, you integrate that area formula, right? So we're going to integrate 3y squared over 4 squared dy. You can distribute that square if you want, but you don't have to solve this, so there's no benefit to it, really. And then we got to think about limits. X-axis or y-axis for this? Which one? Y-axis, right, because we're dy. So that's from, either one would be from 0 up to, what's the y-coordinate at this highest point? 6. And I know that because it's marked over here on that point. So we integrate from 0 to 6. You're not being asked to solve this at all, so that's where you stop. Okay. That cross-section stuff is, it's easy to get it mixed up with what we're doing right now. So I would pay close attention to those as you go through these here. All right, today we are going to be revolving around other axes. So we already did one problem because we did the one from the FRQ assignment. So very similar to what you were doing last night. The only difference is since you are rotating around a line that is not one of the axes, you're going to have, for your like capital R of X and your lowercase r of X, you're going to have different values. So we're going to do setup on these because that's the really important part. I'm not going to try to solve any of these by hand for these because the really important part is the setup. Some of these you may have to do by hand, but on the homework I'm also going to let you just set it up and then type it into the calculator for all of those to make sure you're getting the answer in the back of the book. So volume of the region bounded by x equals 0. X equals 0 is the y-axis. Y equals the square root of x, which is the black graph that we have here. This is y equals the square root of x. And then the line y equals 1 is this line here. So we are looking at this here. Do I mean for this to be y equals 1? Because this really isn't one that goes in this these notes, is it?
Is there supposed to be a hole?
Yeah. So this is one we could have already done, right? Because but we can fix it. Let's make it one that is actually one that we got to look at. Let's say y equals 2, okay? Because this one would not have a hole in it if I left it at y equals 1, and you would only have to do like an outside radius for that, right? You only have to do a capital R. But if I put a y equals 2, which would be this line here, all right, let's add that in up there at the top, and we're rotating around this line. Now I've got to have capital R, lowercase r. There's going to be a hole in the middle of this graph. So I want to do volume of the outside minus volume of the hole. All right. So just like we were doing on the homework last night, we are going to draw a line from the line we're rotating around to the furthest away function, the outside. That's our capital R. Right. So our capital R of X here, we want to do just like we were doing last night. It's going to be whatever you hit at the top minus whatever you hit at the bottom. Right? What do we hit at the top of this capital R? 2. And what do we hit at the bottom? Square root of x. And this is a dx problem because we're rotating around a horizontal line. Okay? So that means for this part, I'm going to have pi radius squared with a dx there. What should the limits be on this problem? Not 0 to 2. 2's on that y-axis. 0 to 1. It's got to come from that x-axis. You okay here? All right, let's do our lowercase r. So that is from the line you're rotating around, that's always where you want to start, to the closest boundary. And this should, well, no, it doesn't have, sometimes it is a straight line, sometimes it's not. So that's our lowercase r of x. What is the top of this line hitting? 2. What is the bottom of this line hitting? 1, which I probably am going to go ahead and simplify that and just make that 1. You don't necessarily have to simplify, but when it's that simple, I usually do. And so now I'm just plugging this in. Pi integral from 0 to 1, 1 squared dx. If it's a free response, I'd stop here. You've got it. If it is multiple choice, there is a pretty decent chance they are going to write it all together. So they'll put the pi, the integral from 0 to 1 here, and then they'll have 2 minus the square root of x squared minus 1 squared dx. And tonight's homework, set it up, type it in the calculator, make sure you getting what the back of the book tells you. You do not have to solve any of these by hand tonight. Okay, let's keep going. All right, here I've got to graph this one. I've got y equals x. That is just a line with a y-intercept at 0 and a slope of 1. So that is y equals x there. I've got y equals 3, which is a horizontal line at 3. Y equals 3 right there. And x equals 0, which is the y-axis. So we're looking at this area right here. And then we are rotating this region about the line y equals 4. So y equals 4 would be up here. And we are rotating around that line. Okay, is this a dy or dx problem? X, because horizontal line, anything horizontal is a dx. So we are doing, like we've done on all of these, volume of the outside minus volume of the whole. So outside radius is going to be from the line you're rotating around to the furthest away point. That's your capital R. So your capital R of x is going to be top of that line. What's it hit? 4. Minus bottom of that line hits x. And so we can just set that up. Pi integral of 4 minus x squared dx. What are limits on this one? Not 4. 3. 0 to 3. So we're looking at the x-axis here. Go 3 there. Okay. Then, for the inside here, we're going from the line we're rotating around to the closest line, right here. This is lowercase r. Lowercase r of x. What am I hitting at the top? 4. What am I hitting at the bottom? 3. Which, since those are just numbers, I'm going to make that 1. And so we get pi integral from 0 to 3 of 1 squared dx. Pretty good chance, multiple choice, puts them together. They will look like this: 4 minus x squared minus 1 squared dx. Yes. Not always. The reason it has been on these last two is because we have a straight line as that boundary. It could be a different value. I wonder if I put one on the next one that is, this will be one I think that's different. Okay. So we've got y equals 2 minus x. So, even though, yeah, I did, okay. Y equals 2 minus x, so y-intercept at 2, slope of negative 1. Then I've got y equals 2 minus 2x. So that's a y-intercept of 2 and a slope of negative 2. Down 2 to the right 1, down 2 to the right 1, down 2 to the right 1. So on like this. And it is the region bounded in the first quadrant. So I was like, there's no bounds here, but it says first quadrant. So we are looking at this little piece right here. And we need to rotate around the line x equals 3. So x equals 3 is, what type of line is that? Vertical or horizontal? Vertical. Vertical line of y equals 3. We're rotating around this line. X equals 3. So since this is a vertical line, what does that tell me I got to do for the problem? It's dy problem, which means both of these equations right here have to get solved for y. So y equals 2 minus x. I'll subtract 2. Y minus 2 equals negative x. Divide by negative 1. Negative y plus 2 equals x. I like to write that as 2 minus y instead. So I'm going to label this blue graph right here x equals 2 minus y. That's what I need to think of. I graph it. Well, it's still solved for y. It's easier to graph, but it's got to be solved for x to use it in the problem. And you got to do the same thing over here. You got y equals 2 minus 2x. Subtract that 2. Y minus 2 equals negative 2x. Divide by negative 2. So you got like negative 1/2 y plus 1 equals x. So you could leave it y minus 2 over negative 2, as long as you don't need to integrate it, like actually do it by hand. Right here. So this line right here is x equals, I'm going to do it 1 minus 1/2 y. But I'm just putting that number first out of preference because I don't like the negatives at the beginning. You can set it up how you would like. So we're doing volume of outside minus volume of the whole. All right. Capital R of X goes from the line you're rotating around to furthest away. That's your capital R. And when so it's going to be R of Y. When you are in terms of Y, we're looking at right minus left. So what do I hit on the right side? That's at 3, right? And then on the left side, I've got the red graph, which is 1 minus 1/2 Y. Now, for simplicity's sake here, I probably would go ahead and distribute that negative. 3 minus 1 plus 1/2 Y, and make that 2 plus 1/2 Y. Mm-hmm.
Is it always right for the two?
Yes. Yeah. Yeah, so when you're looking, if you've got your graph drawn correctly, when you're looking at that capital R line, you're looking at what do I hit on the right side, which is here. There's your 3, right? Because this is X equals 3. And then what do I hit on the left side of that graph?
Sometimes I would do like the outside minus the...
Yeah, you can do outside minus inside. Like through the process of the problem, you're going to be getting negatives. But when you plug it into pi r squared, it gives you positives. So if you do outside minus inside, you can probably still get the right answer. So you're okay with that. It's just like if I plug in a number right here, I would get it, like if I had them backwards, if I want to know what that length of R is, I'd get a negative value. But because pi r squared has a squared in it, it ends up taking care of itself. So if you, there's a little wiggle room here. If you put those backwards, you can probably still get the right answer for that. We okay here? But if you just always do right minus left, like have a system always do right minus left, it'll get you the right answer for sure. Same thing with top and bottom, yeah. If you do bottom minus top, technically you're getting like the wrong signs through if you were like working every step out by hand, but it takes care of itself when you square it, so it doesn't matter. So we got pi integral of the radius 2 plus 1/2 y squared dy. Limits here, 0 to 2, y-axis, right? And so we're out of time, but real quickly, lowercase r right here. So lowercase r of y is going to be 3 minus the other equation, 2 minus y. Distribute here, 3 minus 2 plus y, which is 1 plus y. And so we got minus pi integral from 0 to 2 of 1 plus y squared dy. And you can combine them if you want, but that's fine on the free response. You can leave it. All right, so assignment. You've got 1, 2, 3, 4, 5, 6. Let's see. I will let you skip 2 on this. So any 2 you would like, and you can use the calculator on all of them. Okay, so you may use the calculator on all of them.